Picture the space between two objects, between your hand and the wall across the room, between the Earth and the Moon, between one star and the next. The instinct is to call it empty, not almost empty, not mostly empty, empty in the complete sense, a region where nothing exists, where there is no substance, no activity, no content of any kind, a pure absence. The word vacuum comes from the Latin for empty, and the concept it names feels self-evident. Remove everything from a region of space and what remains is nothing. Nothing is nothing. That seems like the kind of statement that does not need defending. It held up well for a long time. Classical physics had no reason to question it. The vacuum was simply the stage on which matter and energy performed, a neutral background with no properties of its own, no tendency to do anything, no capacity to surprise. Fields existed where sources existed and fell to zero where sources were absent. In the absence of matter and radiation, space was genuinely empty in the sense that nothing was happening, and nothing would happen unless something from outside introduced a disturbance. The vacuum was passive, inert, and complete in its emptiness. This picture is clean. It is also intuitive in the deepest sense, meaning it matches the way ordinary experience presents itself. You do not expect the space between your hands to do anything when you hold them apart. You do not expect a vacuum-sealed container to spontaneously produce content. Emptiness feels stable and final. It feels like the natural resting state of space when matter and energy have been cleared away. The absence of things is not itself a thing. That is the ordinary picture, and it is wrong in a way that took physicists most of the 20th century to fully come to terms with. In 1974, Stephen Hawking followed the implications of that wrongness further than anyone had gone before. He applied quantum mechanics to the region just outside a black hole's boundary and found something that contradicted every intuition the classical picture had built. Black holes, which general relativity described as the most permanent structures in the universe, structures from which nothing could escape and nothing could diminish them, were radiating energy. They were losing mass. They were, on timescales almost impossible to imagine, but nonetheless finite, evaporating. And the thing doing the evaporating was not matter falling in from outside, or some exotic new force acting on the horizon. It was the vacuum itself. Empty space, the passive inert background that classical physics had treated as a neutral stage, was slowly destroying the most extreme gravitational objects in the universe. That prediction did not just change what physicists thought about black holes, it changed what physicists thought about nothing, and understanding why requires going back to the moment when quantum mechanics first looked at the vacuum and found that the classical picture had been wrong from the beginning. But before we get there, a question worth sitting with. If empty space is not truly empty, what is it full of? And how does whatever fills it manage to reach inside something that nothing can escape from? If you like exploring questions like these, feel free to leave a like and subscribe. And if there is something about the universe you find yourself wondering about now and then, let us know in the comments. It might become the next question we explore. For now, let's get back to that question. The answer begins not with black holes, but with the uncertainty principle, and what it says about the minimum possible stillness of any field in nature. A field can never be completely still. Think about a guitar string that has just been plucked. It vibrates. The vibration carries energy, and the string moves visibly above and below its resting position. Now, imagine trying to stop it completely. You press your finger against it, and the vibration dampens. The string settles. But here is the question quantum mechanics asks. Can it ever be perfectly still? Not almost still. not still to any precision a measuring instrument could detect. Perfectly, absolutely, completely motionless. The answer is no. And the reason is not a limitation of technique or technology. It is a fundamental feature of how nature works at the smallest scales. The uncertainty principle, one of the foundational results of quantum mechanics, states that certain pairs of physical quantities cannot both be precisely defined at the same time. Position and momentum are the most famous pair, but energy and time form another pair with the same property. The more precisely you know the energy of a system at a given moment, the less precisely you can know how that energy is changing over time, and vice versa. There is an irreducible fuzziness built into the fabric of reality that no measurement can eliminate and no engineering can overcome. Apply that to a field, not a guitar string, but the electromagnetic field, or the electron field, or any of the quantum fields that physicists use to describe the fundamental constituents of nature. In quantum field theory, every particle is an excitation of an underlying field that permeates all of space. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. And those fields, like the guitar string, cannot be perfectly still. The uncertainty principle forbids it. A field with exactly zero energy at every point at every moment would be a field whose energy was precisely known, and that precision would violate the fundamental fuzziness that quantum mechanics requires. So the fields fluctuate, even in a region of space where there is no matter, no radiation, no source of any kind. The fields are not at rest. They oscillate around zero, dipping above and below, never settling into perfect stillness. The amplitude of these oscillations is small, far too small to detect with any ordinary instrument, but they are real. They contribute to the energy of the vacuum. The vacuum has energy not because something is in it, but because the fields that fill it cannot stop moving. This is called zero-point energy, the minimum energy a quantum field must possess, even in its lowest possible state, and it is not zero. Think of it like the surface of the ocean on what appears to be a perfectly calm day. From a distance, the water looks flat, but if you get close enough, you see that the surface is never truly still. Small ripples appear and disappear. The water is constantly in motion at scales that the eye almost misses. The vacuum of quantum field theory is like that ocean's surface. Viewed from the outside, it appears empty. At the scale where quantum mechanics operates, it is constantly rippling, constantly fluctuating, never at rest. This is not a theoretical abstraction with no measurable consequences. The energy of the vacuum fluctuations has been measured directly in one of the most precisely confirmed experiments in physics. Place two uncharged metal plates very close together in a vacuum, and they attract each other with a measurable force. There is nothing between them, no charge, no current, no field source of any kind, and yet they are pulled together. The force arises because the fluctuating vacuum fields between the plates are constrained by the geometry of the plates, which slightly reduces their energy compared to the unconstrained vacuum outside. The energy difference pushes the plates together. This is called the Casimir effect, and it has been measured with precision that matches the quantum field theory prediction to better than 1%. The vacuum is not empty. The experiment confirms it every time it is run. Empty space fluctuates. Those fluctuations have energy, and that energy, as Hawking would show, is not as passive or consequence-free as the classical picture assumed. Those fluctuations can briefly produce particles. The fluctuating vacuum does something that sounds impossible the first time you hear it. It produces particles. Not permanently, not in a way that violates energy conservation, but briefly, fleetingly, in a way that the uncertainty principle permits before snapping them back out of existence. These are called virtual particles, and they are one of the most misunderstood concepts in all of physics. They are not particles in the sense of tiny, persistent objects moving through space. They are better understood as the vacuum doing something temporary with its energy, borrowing against the future to briefly allow something to exist that has no business existing at all. Here is how to picture it. Imagine you have a strict household budget. Every morning you start with exactly $0, and every night the books must balance back to zero. But during the day, you are allowed to borrow money from tomorrow, spend it, and pay it back before midnight. As long as the debt is settled by the end of the day, nobody notices and nothing permanent changes. The total balance returns to zero and the books close cleanly. Virtual particles are that borrowed money. The vacuum borrows energy from the uncertainty principle's allowance, uses it to briefly create a particle and its antiparticle partner, and then the pair annihilates, and the energy is paid back before the debt becomes permanent. The books close. Nothing lasting has occurred. The particle and antiparticle always appear together because of conservation laws. Electric charge must balance. Other quantum numbers must balance. So the vacuum never produces a single particle alone. It produces a matched pair, one particle and one antiparticle, with opposite charges and quantum numbers that sum to zero, so that the total remains unchanged from before they appeared. They exist for a time so brief that no detector can register them directly. Then they find each other, annihilate, and the energy returns to the vacuum. The process repeats constantly, everywhere in space, at every point, without pause. The vacuum is seething with these temporary pairs appearing and vanishing in a continuous churn of borrowed existence. This sounds exotic, but it has real, measurable consequences beyond the Casimir effect. Virtual particles affect the energy levels of hydrogen atoms in a way that was measured in 1947 by Willis Lamb, a shift in spectral lines now called the Lamb shift. The calculation of this shift using quantum electrodynamics, which includes the effects of virtual particles in the vacuum, matches the measurement to 11 decimal places. Virtual particles are not a metaphor or a convenient fiction. They are a necessary feature of how quantum fields behave, and their effects are among the most precisely confirmed predictions in the history of science. Under normal conditions, the process is self-contained and consequence-free. The pair appears, the pair annihilates, the vacuum returns to its baseline state, and nothing permanent results. The key phrase is under normal conditions. Normal means both particles of the pair exist in the same region of space, with enough time and proximity to find each other and annihilate before the debt comes due. Normal means the vacuum is the same in every direction, with no boundary, no edge, no structure that could separate a pair before they can reunite. Near a black hole, the conditions are not normal. There is a boundary. It is absolute, and it sits exactly where the virtual pairs are doing their fleeting work. When a pair appears close enough to that boundary, the rules that govern their brief borrowed existence change in a way that has no equivalent anywhere else in the universe. One member of the pair can cross that boundary before the annihilation can occur, and once it crosses, there is no coming back. The pair is separated permanently, the debt cannot be repaid in the usual way, and the universe must find another way to balance the books. That boundary is the event horizon. It is not a wall or a surface you could touch. The word boundary is slightly misleading because it suggests a surface you could touch or a wall you could press against. The event horizon is not like that. It is not made of anything. It has no physical substance. If you were falling toward a black hole, you would pass through the event horizon without feeling anything special at the moment of crossing. No jolt, no wall, no sensation of transition. The horizon is not a place where something exists. It is a place where something becomes true. What becomes true at the horizon is this: the escape velocity reaches the speed of light. Escape velocity is the speed something needs to be moving in order to break free from a gravitational field. To escape from the surface of the Earth, you need to be moving at roughly 11 kilometers per second. Get above that speed and you can leave. Stay below it and gravity pulls you back. Every gravitational object has an escape velocity that depends on how massive and how compact it is. A black hole is an object so massive and so compact that at a certain distance from its center, the escape velocity reaches the speed of light. Nothing moves faster than light, so nothing that crosses that distance can ever escape. Not matter, not radiation, not information of any kind. The event horizon is the surface where escape becomes permanently impossible. Think of it like a river flowing toward a waterfall. Far upstream, the current is gentle and a strong swimmer can move against it, swimming upstream and getting away. As the swimmer approaches the waterfall, the current gets faster. At some point, the current matches the swimmer's maximum speed. The swimmer can tread water and stay in place, but cannot make progress upstream. Any closer to the waterfall and the current exceeds the swimmer's speed entirely. From that point on, no matter how hard the swimmer tries, they are carried toward the edge. The event horizon is that point in the river where the current of space-time flowing inward matches the speed of light. Past it, everything flows toward the center, and nothing flows out. What makes the horizon important for what follows is not just what it prevents, but where it sits in relation to the vacuum fluctuations happening just outside it. The horizon is a boundary that exists at a specific location in space. Virtual pairs are appearing and annihilating at every point in the vacuum, including the points just outside the horizon. Most of those pairs appear far enough from the horizon that both members have room to find each other and annihilate normally. But some pairs appear close enough to the horizon that one member is on the wrong side of the line when the pair forms, and for those pairs the situation is irreversible from the first instant of their existence. The horizon has another property that matters here. It is not symmetric. Space outside the horizon and space inside the horizon are fundamentally different regions, in the sense that movement between them is one-directional. Things fall in, nothing comes out. This asymmetry is not a feature of the matter that formed the black hole or of anything special about the center. It is a feature of the geometry of space-time in that region. The curvature of space-time near a black hole is so extreme that the direction pointing toward the center is, past the horizon, not a direction in space at all. It is a direction in time. Falling inward past the horizon is not moving through space toward the center. It is moving forward in time toward an inevitable future. There is no more way to avoid reaching the center than there is a way to avoid the future. That asymmetry is what makes the horizon the critical location for everything that follows. A pair that appears on one side of it and another side of it is not just separated by distance, it is separated by a boundary that makes reunion permanently impossible, and permanent separation changes everything about what the vacuum can and cannot do. Now imagine one of those pairs forming right at that boundary. Picture a pair of virtual particles appearing just outside the event horizon. They blink into existence the way virtual pairs always do, borrowing energy from the uncertainty principle's allowance, appearing as matched partners with opposite quantum numbers, expecting to find each other within the brief window that the uncertainty principle permits, and annihilate back into nothing. Under normal circumstances, that is exactly what would happen. The pair would exist for a fraction of an instant, reunite, cancel each other out, and the vacuum would return to its baseline state as though nothing had occurred. But this pair appeared too close to the horizon. Before the annihilation can occur, before the two partners can find each other and settle the debt, one of them crosses the horizon. Not because it was aimed at the horizon or moving toward it with any particular intent, simply because it appeared close enough that the curvature of space-time in that region, the relentless inward flow of the gravitational field, carried it across the boundary before the annihilation window closed. One member is now inside, one member is outside, and the horizon between them is absolute. Think about what this means for the pair. Their entire existence up to this point has been borrowed. They appeared on credit, expecting to repay the debt through annihilation. The repayment requires both of them. It requires them to meet, to combine their opposite quantum numbers, to release the borrowed energy back into the vacuum. But they cannot meet anymore. The one that crossed the horizon cannot come back out. The one that remained outside cannot go in without itself becoming trapped. The partnership that was supposed to end in mutual annihilation has been broken by a boundary neither of them can cross in the required direction. The outside particle is now stranded. It exists. It is real in the sense that it has energy and momentum and quantum numbers, but it has no partner to annihilate with. The debt it represents cannot be repaid in the usual way, and the universe does not allow debts to go unpaid indefinitely. Energy must be conserved. Quantum numbers must balance. Something has to resolve the situation. The resolution is that the outside particle stops being virtual and becomes real. It is promoted, in a sense, from a temporary fluctuation to a genuine particle with a permanent existence. It moves away from the horizon, carrying its energy with it, and eventually travels outward into space as real radiation. This is Hawking radiation, a real particle produced at the horizon of a black hole, not from any material falling in or any conventional energy source, but from the vacuum itself, from the separation of a virtual pair by a boundary that prevents their reunion. The particle that escapes is real. It carries real energy. It will eventually reach a distant observer as a genuine signal, a photon or some other particle traveling outward from the vicinity of the black hole. What makes this result so striking is that the black hole itself contributes nothing in the conventional sense. No matter flows out. No conventional energy source is tapped. The radiation appears to come from empty space just outside the horizon, produced by the same vacuum fluctuations that occur everywhere in the universe, with the only difference being that the horizon is there to separate the pairs before they can annihilate. The black hole's role is not to emit anything. Its role is to be a boundary, and that boundary, simply by existing, forces the vacuum to produce real particles from nothing. But nothing comes from nothing in physics. The particle that escaped is real and carries real energy. That energy has to come from somewhere, and the only somewhere available is the black hole itself. That energy comes from the black hole itself. Energy conservation is one of the most absolute rules in physics. It does not bend for extreme circumstances. It does not make exceptions for exotic environments. It does not care how strange the situation is, or how counterintuitive the bookkeeping becomes. If a real particle appears outside a black hole's horizon carrying real energy, that energy came from somewhere, and the accounting must balance to the last decimal place. There is no negotiation on this point. The books must close. To see how the accounting works, go back to the pair that appeared at the horizon. The outside particle became real and escaped. The inside particle crossed the horizon and fell toward the center. That inside particle is not a normal particle in the usual sense. Because of the extreme geometry of space-time near the horizon, the particle that fell inward carries what physicists call negative energy relative to an observer far away from the black hole. This is not a loose metaphor. It is a precise statement about how energy is defined in curved space-time, where the geometry itself changes what energy means depending on where you are measuring it from. Think of it like a financial transaction, where one party gains and the other loses by exactly the same amount. The outside particle gains positive energy and escapes. The inside particle carries negative energy and falls into the black hole. The black hole absorbs that negative energy, and absorbing negative energy is mathematically identical to losing mass. The black hole gets lighter by exactly the amount needed to account for the energy carried away by the escaping particle. The books close perfectly, energy is conserved, the universe's accounting is satisfied. This is the mechanism by which Hawking radiation costs the black hole its mass. It is not that the black hole is leaking material through the horizon, the way a balloon leaks air through a pinhole. Nothing crosses the horizon outward. The horizon remains a one-way boundary in the strictest sense. What happens instead is that the vacuum just outside the horizon produces real particles at the black hole's expense, with each escaping particle representing a withdrawal from the black hole's mass account that can never be reversed. Imagine owning a savings account with a very unusual bank. Every day the bank is required by law to give a small amount of money to a random stranger on the street outside. The money does not come from the bank's own reserves in any direct sense. It comes from your account automatically, whether you authorize it or not. You never see the transaction happening. You never interact with the stranger. But every day your balance is slightly lower. Over a very long time, if the withdrawals continue, the account empties. The black hole is that account. The escaping Hawking radiation particles are the strangers receiving the withdrawals, and the vacuum at the horizon is the mechanism the bank uses to make the transfer happen without anything physically crossing from your account to the street. The rate of mass loss is extraordinarily slow for the black holes that exist in the universe today. A stellar mass black hole, the kind formed when a massive star collapses at the end of its life, loses mass to Hawking radiation at a rate so small that it would take far longer than the current age of the universe to lose even a tiny fraction of its mass. The radiation is real, but the effect is, for now, unmeasurably small for any black hole we know of. The principle, however, is absolute. Every black hole is losing mass. Every black hole is, on some timescale, temporary, and the smaller a black hole gets, the faster it loses mass, because the rate of Hawking radiation depends directly on the black hole's size in a way that accelerates as the black hole shrinks. Which raises an immediate question. If the radiation has a rate, and that rate depends on the black hole's size, then the radiation must have a temperature, and a temperature means something very specific and very surprising about what kind of object a black hole actually is. That radiation has a temperature. In physics, temperature is tied directly to radiation. Any object with a temperature above absolute zero emits radiation, not because it is burning or reacting chemically, but simply because it is warm. The hotter the object, the more intensely it radiates, and the shorter the wavelength of the radiation it produces. A piece of metal heated gently glows red. Heated more intensely, it glows orange, then yellow, then white. The color is a direct readout of the temperature. This relationship between temperature and emitted radiation is called black body radiation, and it is one of the most fundamental and precisely understood phenomena in physics. When Hawking calculated the properties of the radiation being produced at the black hole's horizon, he found something that stopped him. The radiation was not random. It was not a chaotic spray of particles with arbitrary energies. It had a specific, well-defined spectrum, meaning the distribution of energies among the escaping particles followed a precise mathematical curve, and that curve was identical to the curve of black body radiation. The radiation coming from the horizon of a black hole had exactly the same mathematical shape as the radiation coming from a warm object sitting in a room, which meant the black hole had a temperature. Think about what that implies. A black hole is not a warm object in any conventional sense. It is not made of atoms vibrating with thermal energy. It is not burning. It is not reacting. It is a region of space-time where gravity has become so extreme that nothing can escape, and yet the radiation emerging from its vicinity has a temperature as precisely defined as the temperature of a piece of glowing metal. The mathematics was unambiguous. Hawking calculated the exact value. The temperature of a black hole is inversely proportional to its mass. A more massive black hole has a lower temperature. A less massive black hole has a higher temperature. To feel how extreme these temperatures are, consider a stellar mass black hole, one with roughly 10 times the mass of the Sun. Its Hawking temperature is approximately 100 millionth of a degree above absolute zero. That is so cold it makes the coldest regions of outer space, which sit at about 3 degrees above absolute zero due to the cosmic microwave background radiation left over from the early universe, feel blazing hot by comparison. A stellar mass black hole is the coldest object in the universe by a very large margin. Its Hawking radiation is so faint and so cold that detecting it against the background radiation of the universe is currently impossible with any technology that exists or is foreseeable. But here is what I find genuinely striking about this. The temperature is not an approximation or an estimate. It is an exact result derived from first principles, combining general relativity, quantum mechanics, and thermodynamics in a single calculation. 3 of the most powerful frameworks in physics. Frameworks that physicists had spent decades trying and failing to reconcile with each other, produced a single clean number when applied simultaneously to the black hole horizon. That number had units of temperature. The universe was telling physicists something through that result, something about a connection between gravity and heat that nobody had anticipated and that the existing frameworks had no language to describe. The smaller the black hole, the hotter it is. A black hole with the mass of a mountain, far smaller than any black hole formed by stellar collapse, would have a temperature of billions of degrees and would be radiating intensely. A black hole with the mass of a large asteroid would be radiating gamma rays at temperatures beyond anything achievable in any laboratory. These primordial black holes, if they exist, would be the hottest objects in the universe, and they would be shrinking rapidly, their temperature rising as they lost mass, in a feedback loop that accelerates toward a final explosive endpoint. That endpoint, and what it means for the information that fell in, is one of the deepest unsolved problems in physics. But before reaching it, there is something else the temperature implies. Something that connects black holes to a branch of physics nobody expected them to have anything to do with. That temperature means black holes behave like thermodynamic systems. There is a branch of physics called thermodynamics that was developed in the 19th century to understand heat engines, steam power, and the flow of energy through mechanical systems. It produced 4 laws that turned out to be among the most universal statements in all of science. The first law says energy is conserved. The second law says entropy, the measure of disorder in a system, always increases or stays the same in any closed system. It never spontaneously decreases. The third law says you can never reach absolute zero temperature through any finite sequence of steps. These laws were derived from the behavior of gases and engines. They were not supposed to have anything to say about black holes. And yet, in the early 1970s, before Hawking's calculation, a young physicist named Jacob Bekenstein noticed something uncomfortable about black holes in the second law of thermodynamics. The second law says entropy always increases. Entropy is roughly a measure of how many ways a system can be arranged internally while still looking the same from the outside. A highly ordered system has low entropy. A highly disordered system has high entropy. Drop a cup of hot coffee into a cold swimming pool, and the heat spreads through the water, increasing the disorder of the system, increasing the entropy. That process is irreversible. The entropy of the combined system never spontaneously decreases. But what happens when you drop something into a black hole? From the outside, a black hole looks the same regardless of what fell into it. You can throw in a library of books, a cloud of gas, or a collection of perfectly ordered crystals, and the black hole responds the same way in each case. Its mass increases, its horizon grows slightly, and all the information about what you threw in, all the order, all the structure, all the low entropy content of the infalling material appears to vanish. If entropy is a measure of information and structure, and black holes destroy information and structure, then throwing things into black holes should decrease the total entropy of the universe, and that would violate the second law. Bekenstein's resolution was elegant and slightly unsettling. He proposed that black holes themselves carry entropy, not zero entropy, not a small amount of entropy, but an enormous amount of entropy proportional to the area of their event horizon. The surface area of the horizon, measured in units of the Planck length squared, the smallest meaningful length scale in physics, gives the entropy of the black hole directly. When you throw something into a black hole, the horizon grows, the surface area increases, and the entropy of the black hole increases by at least as much as the entropy of whatever fell in. The second law is saved because the black hole's own entropy absorbs and exceeds the entropy of the infalling material. Think of it like a very deep and very messy filing cabinet. You have a stack of perfectly organized documents on your desk, carefully sorted and labeled, representing a low-entropy, highly ordered system. You throw them into the filing cabinet unsorted. The documents are now part of a vastly more disordered system. The total entropy of the room has increased. The order that was in the documents has not been destroyed. It has been absorbed into a much larger disordered system, where it is effectively inaccessible. A black hole does something similar but more extreme. The order that falls in is absorbed into the enormous entropy of the horizon, lost in the most inaccessible filing cabinet the universe possesses. When Hawking's temperature arrived, it snapped into place alongside Bekenstein's entropy, like two pieces of a puzzle that were always meant to fit together. A temperature and an entropy together define a thermodynamic system completely. Black holes had both. And once they had both, the full set of thermodynamic laws could be written down for black holes in a form that mirrored the original laws almost perfectly. The zeroth law of black hole thermodynamics said the surface gravity of a black hole is constant across its horizon, the way temperature is uniform across a system in thermal equilibrium. The first law connected changes in mass to changes in entropy and angular momentum, the way energy conservation connects heat and work. The second law said the total horizon area never decreases, mirroring the entropy law. The third law said you cannot reduce the surface gravity to zero in a finite number of steps. What I find most remarkable about this is that these laws were written down before Hawking's calculation confirmed that the temperature was real. Bekenstein and others had constructed the thermodynamic framework for black holes as a mathematical analogy, useful but possibly just formal. Hawking's result showed it was not an analogy. It was the actual physics. Black holes are thermodynamic objects in the fullest sense of the term. They have real temperatures and real entropy, and they obey the same fundamental laws that govern steam engines and refrigerators and every other thermodynamic system in the universe. The question that followed was unavoidable. If black holes have temperature and entropy, and they are slowly losing mass to Hawking radiation, what happens when the mass runs out entirely? That mass loss accelerates over time. A black hole losing mass to Hawking radiation is like a block of ice sitting on a warm surface. The ice melts slowly at first, losing mass at a steady rate determined by the temperature difference between the ice and the surface. But as the block gets smaller, something changes. A smaller block has more surface area relative to its volume, which means more of it is exposed to the warmth relative to how much ice remains. The melting accelerates. The smaller it gets, the faster it shrinks. The final moments of the block's existence are not a gentle continuation of the earlier slow melt. They are rapid collapse, the last sliver of ice disappearing in a fraction of the time it took to get to that point. Hawking radiation follows exactly this pattern. The rate at which a black hole loses mass depends on its temperature. The temperature depends inversely on its mass. A massive black hole is cold and radiates slowly. As it loses mass, it gets slightly less massive, which makes it slightly warmer, which makes it radiate slightly faster, which makes it lose mass slightly more quickly. The process feeds back on itself in a loop that accelerates continuously. The more mass the black hole loses, the faster it loses the remaining mass. The curve of mass loss over time is not a straight line declining steadily to zero. It is a curve that stays nearly flat for an almost incomprehensibly long time, and then plunges steeply to zero in a final burst. For the black holes that exist in the universe today, the timescales involved are staggering. A stellar mass black hole with roughly 10 times the mass of the Sun would take approximately 10 to the power of 74 years to evaporate completely through Hawking radiation. To put that number in context, the current age of the universe is approximately 14 billion years, which is roughly 10 to the power of 10 years. The evaporation timescale for a stellar mass black hole is therefore longer than the age of the universe by a factor of 10 to the power of 64. That is not a large number in the everyday sense. It is a number so large that writing out all its digits would require more space than exists in the observable universe. The black hole will outlast every star, every galaxy, every structure the universe currently contains by an almost incomprehensible margin, and it will still be there, cold and dark and slowly shrinking, long after everything else has dissipated. Smaller black holes evaporate faster. A black hole with the mass of a mountain would evaporate in roughly the current age of the universe, meaning that if any mountain mass black holes were formed in the early universe, they would be reaching the end of their lives right now, their final moments producing a distinctive burst of high-energy radiation that physicists have searched for but not yet detected. A black hole with the mass of a large asteroid would have evaporated long ago, its entire existence compressed into a brief violent flash in the early universe. The final moments of any black hole's life are where the physics becomes most extreme and most uncertain. As the black hole loses mass, its temperature rises. As the temperature rises, the radiation becomes more energetic. As the radiation becomes more energetic, the mass loss accelerates further. In the final fractions of a second before the black hole reaches zero mass, the temperature is climbing toward values that exceed anything in the known universe. The radiation in those final moments is not the cold whisper of microwave photons that a stellar mass black hole emits. It is a violent burst of high-energy particles across every available channel, a final explosive release of everything the black hole had been quietly accumulating and slowly spending over its entire existence. What happens at the very end, at the precise moment when the mass reaches zero, is something current physics cannot answer. The equations that describe Hawking radiation break down as the black hole approaches the Planck mass. The scale at which quantum gravity effects become dominant and the frameworks physicists currently have become unreliable. Whether the black hole disappears completely in a final explosion, leaves behind a stable remnant too small for current theory to describe, or does something else entirely that requires a theory of quantum gravity to understand, remains genuinely unknown. It is one of the open questions that Hawking radiation places most sharply on the table. But the final explosion is not the deepest problem the evaporation raises. The deeper problem is about what happens to everything that fell in, and that problem does not wait for the final moment. It is present from the first particle that ever crossed the horizon. And that deeper problem is the information paradox. Imagine writing a letter, not a short note but a long, detailed letter containing everything about you, your memories, your personality, your history, every thought you have ever had written down in full. You seal it in an envelope and drop it into a black hole. The envelope crosses the horizon. It falls toward the center. From that moment on, according to general relativity, it is gone. Not gone in the sense of being inaccessible or hard to retrieve. Gone in the sense that the information it contained has left the observable universe entirely and can never influence anything outside the horizon again. Now, wait for the black hole to evaporate through Hawking radiation. Eventually, after an almost incomprehensible stretch of time, the black hole loses all its mass and disappears. The horizon shrinks to nothing. The region of space-time that was once inside the black hole ceases to exist in any meaningful sense, and the letter and everything else that ever fell in, every particle, every quantum state, every piece of information that crossed the horizon over the black hole's entire lifetime, is simply gone. Not transformed, not scrambled into an unreadable form, but still present somewhere. Gone. That is the information paradox, and to understand why it is a paradox rather than just an unfortunate situation, you need to understand what quantum mechanics says about information, and why losing it permanently is not just inconvenient, but physically impossible. In quantum mechanics, every physical system is described by a quantum state, a precise mathematical object that encodes everything about the system at a given moment. The laws of quantum mechanics are designed so that quantum states evolve in a specific way over time. Given the state of a system now, the laws tell you exactly what the state will be at any future time, and equally importantly, they tell you exactly what the state must have been at any past time. The evolution is reversible. Information is never created or destroyed. It is only transformed, scrambled, rearranged, but always in a way that is in principle reversible. If you knew the complete quantum state of all the Hawking radiation that a black hole ever emitted, you should in principle be able to run the calculation backward and reconstruct everything that ever fell in. The letter, in all its detail, should be recoverable from the radiation, in principle, no matter how scrambled. But Hawking radiation does not work that way. The radiation that emerges from the horizon is thermal. It is the quantum equivalent of random noise, a featureless distribution of particles whose properties are determined entirely by the black hole's temperature and nothing else. It carries no imprint of what fell in. A black hole that swallowed your letter and a black hole that swallowed an equivalent mass of hydrogen gas would produce identical Hawking radiation. The two situations are physically different. The quantum states of the infalling material were different, but the outgoing radiation is the same. The information about the difference has been erased. Think of it like burning a book. In principle, if you could collect every single photon and particle produced by the fire, every wisp of smoke, every ash fragment, and run the laws of physics perfectly backward, you could reconstruct the book from the products of its burning. The information is scrambled, but not destroyed. It is still present in the correlations between the particles. Hawking radiation is not like that. It is more like a copying machine that produces the same blank page, regardless of what document you feed into it. The output contains no information about the input, and when the machine switches off at the end of the black hole's life, the original document is gone with no copies anywhere. This creates a direct conflict between general relativity and quantum mechanics. General relativity says the horizon is a one-way boundary, and what falls in stays in until the black hole evaporates, at which point it is simply gone. Quantum mechanics says information cannot be permanently destroyed under any circumstances. Both statements cannot be simultaneously true. One of the most successful theories in the history of science is wrong about something fundamental, and Hawking radiation is the place where the contradiction is most sharply visible. That contradiction is not a technical detail waiting for a small correction. It is a deep structural incompatibility, and resolving it requires understanding something about quantum mechanics that makes information loss so completely unacceptable that physicists have spent decades searching for any alternative. In quantum mechanics, information cannot be lost. There is a principle at the heart of quantum mechanics called unitarity. It is not a law that was discovered by accident or confirmed through a single experiment. It is a structural requirement that the entire mathematical framework of quantum mechanics is built around. Remove unitarity and quantum mechanics does not just become less accurate, it becomes incoherent. Probabilities stop adding up to 1. Predictions become meaningless. The theory collapses from the inside. Unitarity says this: the total probability of all possible outcomes of any quantum mechanical process must always equal exactly 1, not approximately 1, not 1 on average, exactly 1 at every moment, under every circumstance. This seems like a reasonable bookkeeping requirement, but its implications run much deeper than bookkeeping. It means that quantum mechanical evolution is perfectly reversible. Given the final state of a system, you can always reconstruct the initial state. No information is ever permanently lost. It is only ever transformed. Think of it like a perfectly shuffled deck of cards. You start with the cards in a specific order. You shuffle them through a long sequence of cuts and riffle shuffles. The order looks random. To a casual observer, the original arrangement appears to be gone, but every shuffle is a reversible operation. If you knew every shuffle that was performed, in what order, with what exact motion, you could unshuffle the deck and recover the original arrangement perfectly. The information about the original order was never destroyed. It was encoded in the sequence of shuffles, present in the final arrangement in a scrambled but recoverable form. Unitarity says the universe works like that deck. Every process is a shuffle, never a burning. Now consider what happens if Hawking radiation genuinely destroys information. A black hole forms from a specific configuration of matter in a specific quantum state. It evaporates over an enormous stretch of time, emitting thermal radiation that carries no information about that initial state. At the end of the evaporation, the black hole is gone. The initial quantum state is gone. The radiation that remains is the same regardless of what the initial state was. The mapping from initial state to final state is not reversible because multiple different initial states all produce the same final state. Unitarity is violated. The total probability of all outcomes no longer adds up correctly. Quantum mechanics breaks down. This is not a small problem. It is not the kind of discrepancy that gets resolved by adding a correction term to an equation or refining a measurement. It is a statement that one of the two most successful physical theories ever constructed is fundamentally wrong about something at a deep level. Either general relativity is wrong about the horizon being a perfect one-way boundary, or quantum mechanics is wrong about information being perfectly conserved, or both are approximations to some deeper theory that resolves the conflict in a way neither framework can currently express. What makes the paradox so difficult is that both theories are extraordinarily well confirmed in their respective domains. General relativity has been tested to extraordinary precision in everything from the orbit of Mercury to gravitational wave detection. Quantum mechanics underlies every transistor, every laser, every chemical reaction, every piece of technology built in the last century. Neither theory shows any sign of breaking down in any experiment ever performed, and yet applied simultaneously to a black hole, they produce a contradiction that neither can resolve on its own terms. Hawking himself initially believed that information was genuinely destroyed, that the universe was not perfectly reversible at the quantum level, and that black holes represented a genuine exception to unitarity. He held that position for decades before eventually conceding in 2004 that information was probably preserved somehow, though the mechanism remained unclear. The concession was significant, not because Hawking was infallible, but because it reflected how seriously the theoretical community had come to take the unitarity requirement. Losing information permanently is not just philosophically uncomfortable, it breaks the mathematical machinery that makes quantum mechanics work. The paradox demanded a resolution. Several have been proposed, none has been confirmed, and each proposed resolution comes with its own set of uncomfortable consequences that reveal just how deep the conflict runs. So how can that contradiction be resolved? When a physics problem resists solution for decades, the range of proposals tends to reveal the depth of the issue more than its answer. The black hole information paradox has attracted intense effort for over 50 years, producing ideas that are each compelling in some ways and unsatisfying in others. The lack of consensus suggests the conflict between general relativity and quantum mechanics at the horizon is not superficial, but structural. The most conservative proposal is that information is not destroyed, but encoded in subtle correlations within Hawking radiation. The radiation appears thermal and random, but it may carry hidden patterns that preserve the original information, like a message concealed in noise. This idea, associated with Don Page and later supported by Stephen Hawking, preserves unitarity without changing existing theories. The problem is that no clear mechanism explains how this encoding works. The horizon remains locally unremarkable, so any leakage of information must be extremely subtle while still encoding everything that fell in. A more radical proposal suggests that black holes leave behind stable Planck scale remnants after evaporation. These remnants would store all the information internally. The difficulty is that this requires an object smaller than an atom to contain arbitrarily large amounts of information, implying an effectively unlimited number of internal states, which conflicts with established principles. The most dramatic proposal is the firewall, introduced in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully. It argues that preserving unitarity forces the horizon to become a high-energy boundary that destroys anything falling in. Instead of passing through smoothly, the infalling observer encounters a violent barrier. While mathematically consistent, this violates the equivalence principle of general relativity, which predicts nothing unusual at the horizon. Each proposal saves one aspect by sacrificing another. Hidden correlations lack a mechanism, remnants require unlimited complexity, and firewalls abandon a core principle of relativity. The paradox remains unresolved, but its structure is now clearer, pointing to a deeper problem in our understanding of space-time itself. There is another clue hidden in how different observers see the vacuum. There is a related prediction worked out by William Unruh in 1976 that takes the strangeness of the quantum vacuum one step further. Unruh asked a simple question. If a black hole horizon causes the vacuum to produce real particles for a stationary observer outside it, what does an accelerating observer detect in a vacuum that a stationary observer sees as completely empty? The answer was that an accelerating observer detects thermal radiation, not because anything is emitting radiation, not because the vacuum has changed, but because the accelerating observer and the stationary observer do not agree on what the vacuum is. This is genuinely strange. Two people in the same region of space, surrounded by the same quantum fields. The stationary one measures the vacuum and finds it empty. The accelerating one measures the same vacuum and detects a warm bath of thermal particles. Same location, same fields, different observers, different measurements of what is there. Think of it like two people reading the same page through different lenses. One lens is flat and shows the words clearly. The other distorts the page in a way that makes new patterns appear. Neither person is wrong, but what they see is genuinely different. The vacuum is like that page. What you find in it depends on how you are moving through it. The connection to Hawking radiation is direct. The horizon of a black hole creates a relationship between the regions on either side of it that is mathematically identical to the relationship between an accelerating and a stationary observer. The Hawking temperature and the Unruh temperature are two expressions of the same underlying fact. The vacuum responds to geometry and acceleration in a way that produces real thermal effects for real observers. Nothing is not nothing. That conclusion, which began as a correction to classical intuition, has become one of the most precisely quantified results in modern physics. What Hawking radiation changed was not one theory, but the boundary between three of them. Before 1974, the three great frameworks of modern physics occupied separate territories. General relativity described gravity and the large-scale structure of space-time. Quantum field theory described particles and fields at the smallest scales. Thermodynamics described heat, entropy, and the flow of energy through macroscopic systems. Each was extraordinarily successful in its own domain, and each was, in important respects, incompatible with the others. Hawking radiation forced the overlap. It was the first result in physics that required all three frameworks simultaneously. To derive it, you need general relativity to describe the horizon. You need quantum field theory to describe the vacuum fluctuations. You need thermodynamics to interpret the thermal spectrum, and connect it to temperature and entropy. Remove any one of the three and the calculation cannot be done. That intersection had never been explored before. Physicists knew abstractly that gravity and quantum mechanics would eventually need to be reconciled, but the place where that reconciliation was most urgently needed had not been identified with any precision. Hawking radiation identified it. The black hole horizon is where the three frameworks meet most directly, and where their incompatibilities are most sharply exposed. What changed was not the content of any framework. General relativity still works. Quantum mechanics still works. Thermodynamics still works. What changed was the understanding of where their boundaries lie. Any theory of quantum gravity must derive Hawking radiation from first principles. It must resolve the information paradox. It must explain the final moments of evaporation. These are not vague requirements. They are sharp tests that any candidate theory must satisfy. Hawking made this prediction without any experimental guidance, working purely from the internal logic of combining frameworks never designed to be combined. The vacuum was always destroying black holes. He was simply the first to follow the reasoning far enough to see it.